here you have
birational invariance mean? What does birational invariance mean?
so these are invariants which are preserved under birational transformations.
What?
Invariants which are preserved under birational transformations. In other words, they are only invariants of the field of functions associated with projective varieties.
What is
Fields of functions.
what?
Fields of functions.
Field
Fields of
of
rational functions. Or like fields of homomorphic functions associated with projective varieties.
The field of paramorphic functions. So the variance of that field. Okay. Does it mean something geometrically?
So that's what the goal of the talk is, that they actually are related to two different geometric theories in this particular talk. One of them is Koch theory, classical one.
Does the definition mean something geometric?
So that they are, in the case when these are going to be proclaimed to be rational varieties, this means that there is a dominant map on the Pn of this variety. Map which
So
says
that's true for any algebraic.
no, degree 1, Pn, not every variety. If they are rational, there will be a dominant map from this variety.
Little dominant now.
This means that it sends an open heuristic topology set.
What?
So this means that there is a map which sends an open set, regular map which sends an open set of this variety into the of Pn to this variety.
That has its properties. Open is just
As I
open.
said, regular.
Huh?
Regular.
What?
Regular. It's given by
Dennis?
What?
Dennis? Let him show his first slide first before you ask him.
Yeah. In any case, so Dennis, if you want, I can give you a course in algebraic geometry after I finish my talk, or refer you to the book by
Well, I worry about the audience. I'm asking questions that I think some people don't know here.
Yeah, I'll try to introduce them to.
Okay.
So now, as I said, so the idea is that we actually combine two different theories and draw some invariants out of this combination. So the main example that I'll be concentrating on is combining classical Koch theory with Gromov-Witten invariant. But you can change this to combining classical Koch theory with Chen-Wang homology or Chas-Sullivan homology and get new invariants as well, but that will be a subject of different talks. So now, as in the same way as topology studies manifolds in connection with spheres, variational geometry or algebraic geometry in general studies smooth projective varieties in connection with the simplest one, and these are the projective spaces. So we will say that an algebraic variety is rational over the complex numbers if the field of rational functions of this variety is the field of rational functions of n independent variables where n is the dimension of x. So in particular, if this is P1, the corresponding field of rational function is just the field of rational functions of one variable. And now, in a way, this can be done in a pictorially in a relatively simple way. So if we are in the case when our manifold X is just a conic in P2, still given by degree 2 polynomial. So this variational map, in the case of conic, is just a projection from a point. And we see that we have one-to-one correspondence between the complex line and an open subvariety in this conic. And that is true for all quadrics in any dimension. If it has a point or the corresponding field, then there is such a projection, so you get this dominant map. So what happens if we consider actually curves of degree 3? So obviously, such a projection doesn't give us a one-to-one map, so it's 2-to-1 generically, and so we cannot claim that there is a one-to-one correspondence between open set in this curve and C. And it is known that these curves of degree 3 are not rational, and there is a homological abstraction to this known to Abel and Riemann, and this is the fact that the first Cauchy number H10 is equal to 1, and that is certainly 0 for P1. So that is the first example of something which is not rational, meaning there is no rational map to P1, and the abstraction of this is this transcendental number H10. So now, a natural question is what is happening with other cubic hypersurfaces in Pn. So for the quadric ones, we said that they are all rational. And so now, of course, there is a lot of history into this. So if you look at this hypersurface in P3, so it is known that it is variational to P2, and that belongs to Marquis Campo di Sola, who actually has shown this. Actually, he was also a mayor of Naples for quite some time. But in mathematics, his name is Pasquale del Pezzo. So, and he actually has shown that this surface here can be obtained from P2 by the following procedure. So you take 6 points in general position, and you, instead of these points, put a line there. Do this surgery, and then this surface here, given by this equation, is obtained from P2 by this blow-up procedure. So a blow-up procedure is very common in birational geometry. So not only in dimension 2, but entire dimension as well. So you replace certain submanifold like points in here by the corresponding utilization of the normal bundles to these subvarieties, and this surgery that you are performing actually is a very common variation in variational geometry, and all of the variational transformations can be obtained as a sequence of blowing up of points or subvarieties in higher dimensions and blow down. So that's the main way to think geometrically of what variational transformations are. So to answer Dennis's questions, that's what we are trying to answer. Is our manifold X obtained from P2 by sequence of this geometric procedure, these surgeries, blowing up in subvarieties and then blowing down? So that is the geometric question we are trying to answer. So now, we saw that in dimension 2, that is certainly true over the field of complex numbers. So by the end of the talk, I'll try to show you that actually if you change the field, that is not even true for the cubics in dimension 2. But there is one other thing that I would like to demonstrate, and that is that if my cubic is singular, you definitely can produce a map from this cubic to the line. This is in one dimensional case, but it's true in any dimension, in a way that is good. So these singular cubics are rational, but it's also bad because the most successful argument of studying non-rationality is by deforming to something which is singular and getting some abstraction to this singular thing. But it's rather clear that in the cubic case that won't work, because this cubic property given by this equation is not going to be possible to take by this kind of invariance, because already deforming it into the singular ones, we get something that is rational. So let's move in the rational way of developing the variational geometry. So we go one dimension higher, and that is dimension 3. And already here we encountered some difficulties. So it has been an open question in algebraic geometry if smooth three-dimensional cubic over the complex number is rational or not. And that actually was proven at the beginning of the 70s, I believe in 1972, by Clemens and Griffiths. And again, they introduced a very involved invariant, and that is so-called intermediate Jacobian. So you take the plural of H21 homology group associated with this cubic, and you mod out by the embedding of the third homology by integration. And so this abelian variety that obtained as a quotient is called intermediate Jacobian. And so now there is a deeper study of the properties of this intermediate Jacobians, going back to Mumford and even before that to Andreotti and Meyer. And so it was Andreotti and Meyer who pointed out that there are some singularities tentative either associated with this, which cannot be of very big codimension. And then Mumford spent quite a bit of time studying the geometry of the prime varieties. So all we need to answer in this question, in this situation, is if this three-dimensional cubic is obtained from P3 by a blowing up curve And if you look at the Hodge diamond of this three-dimensional cubic, it looks very much that we have a candidate for this curve, a curve of genus 5 here, because this is exactly how the Hodge diamond of the curve of genus 5 looks like. But a deeper analysis that was carried by Clemens and Griffiths using the theory of Andreotti-Meyer and Mumford shows that this actually is not come from a Jacobian of a human surface of genus 5 due to the fact that some singularities that the divisor has rather big codimension, in this case, codimension 5. And this was a Jacobian of a curve, this was one of the only codimension for most. So now this is the classical knowledge of birational geometry of the cubics. So until very recently, not that much was known about cubics in higher dimension. A lot of work was done on the four-dimensional cubic, and so probably the world expert in the modular space of cubic is here, Serrano. There is a wonderful work by Katzarkov on the subject, and some people propose to use derived categories, Kuznetsov, Berry, and so on and so on. But the approach that I'll propose here is definitely motivated by information coming from mirror symmetry. But at the end of the day, we'll try to avoid the use of mirror symmetry and restrict ourselves to something which is called theory of atoms. I mean, initially, I really hated this name, but it turns out that there are higher invariants which look like Mendeleev tables and isotopes, and that actually is going to appear in a paper coming very soon. So it turned out that no matter initially it was not a great name if you ask me, eventually was a really good one. So any questions?
Who suggested?
It was Maxim. It wasn't, but he didn't know about Mendeleev tables and about isotopes at that time. But he had this hinge. So in any case, now, as I said, we'll enhance this picture a little bit by adding information of mirror symmetry, and we'll keep these examples of two- and three-dimensional cubic throughout all the talks and coming back to them to decide really they are going to be our reference point for introducing these new approaches. So I would like to mention that there are some fantastic papers, some fantastic work that has been completed in that direction by different groups of people. Certainly, I already mentioned the work of Clemens and Griffiths. There was an approach with the torsion group of the homology group by Artin and Mumford. So there was an approach using the study of the group of birational dimorphism by Miskowski and Manin. So the generation study chose zero, that was a technique introduced by Boazan, and then later developed by Bohr, Birutke, Boulot-Thielen, many other people. I'm sorry, I'm omitting a lot of names here. And then there were analytic methods by multiplier ideal shifts, and so that's an idea of NATO, later really developed by Ein and Lazarsfeld, who actually gave a new proof of the non-relationality of three-dimensional particle using multiplier ideal shifts. And later on, this was fully explored by possibly Fernex in higher dimensions. But the method that we're discussing here is completely different, and it's we'll have one final goal at this talk to really study the case of four-dimensional smooth cubic. So this is a cubic hypersurface in P5, and try to answer this question: does it come as a sequence of blow-ups and blow-downs from P4? If the time permits, I'll say a couple of words about the five-dimensional cubic as well. All right, so now, as I said, the new ingredient of this approach will be ideas coming from mirror symmetry. And so, as I pointed out, the main building blocks of birational transformations are this blow and blow downs. So what I will propose is to look at this building blocks from a little bit different perspective and try to get additional information. So I'll be very vague here and try to go in very elementary way. So the mirror symmetry basically corresponds to different models to the same variety. One is we think of this variety as an algebraic variety, as let's say hypersurface in Pn, as some of these show. And the other is we associate so-called A model, a symplectic manifold, with certain category associated with it. So on one side we have an algebraic variety, like P2, and on the other side we have a symplectic variety, in this case, a symplectic manifold C2, with this potential in it. And to this symplectic manifold, we associate a category of Lagrangians, and to the algebraic variety, we associate a category of complexes of coherent sheaves. And so we want to study the birational properties of these varieties, and the way to try to do that is by studying the singularities of this function that appears here. So we want to study P2, or the corresponding algebraic variety, and we replace birational geometry by properties and the singularity theory of this function associated with this manifold. So in order to do that, we need to see how birational transformations affect our manifold, in this case P2. So the Horst diamond of P2 is this 1, 1, 1 at H0, H2, and H4. And so now the corresponding function on C2 that we associate with P2 is this function W, this round polynomial, x plus y plus 1 over xy. So if you clear the denominators, you just easily find out that this function is generically, its generic fiber is open elliptic curve, the curve of minus 1, minus 3 points, and we have 3 singular fibers associated with this vibration. So now, as we said in the case of P2, birational transformations are blow-ups and blow-downs of points. Let's see what a blow-up is going to give us in this situation. So if I blow up P2 in one point, then the Horst diamond becomes 1 to 1. And what's happening with the corresponding mirror function is that actually we create one additional singular fiber. So blow up of a point on P2 creates one additional singular fiber in the corresponding A side. So new singularity corresponds to this blown up manifold. And so now the whole point here is to try to find a way so that these new singular fibers do not interfere with what we already have. So now if I blow up 6 points, as in this example of two-dimensional cubic, we just add 9, we add additional 6 singular fibers. So in such a way, once again, birational geometry is translated to a theory of singularities, and that is the main point of this observation by the use of mirror symmetry in this case. So now we can go a little bit deeper in that direction. So let's spend a little bit of time looking at our other favorite example, and that is the example of three-dimensional cube, the one that was taken by Clemens and Green's. So in this case, the manifold on the so-called A side is C3, and then we have this function x plus y plus z to the third, or x, y, z plus z on this manifold C3. So now, if you compute the singularities, you will see that this function has generically an open surface as a generic fiber, and we have 3 singular fibers. So 2 of them are just already double points, and then we have a very big singularity consisting of intersection of 6 surfaces, 6 rational surfaces. So 3 of them intersect in open book configuration, and then 3 others intersect this configuration transversely. And so you can actually try to see what is this geometry of this vibration, what is the information that is hidden in this singularity, and then indeed the first thing to try to do is to compute the hyperhomology of these periodic vanishing cycles, and you'll see that in a way you recover the homology of your initial cubic, but with some changes. So the fourth diamond of the three-dimensional cubic was given by this, and then indeed you get, if you go to the hyperhomology, that you actually get the homology of the cubic with some rotation and shift. But you can go a little bit deeper and look at the information that this singularity is actually carry. And so what you could study is homodromy, another important part of studying the singularities, around this very singular fiber. And you will notice that the monodromy operator acting on the singularity at this very singular fiber are actually given by a diagonal matrix which is 3 by 3 due to the fact that the incidental part is rank 3. And this matrix on the diagonal has numbers 1, epsilon, and epsilon squared. So now, if you study all A side, standard input model, so-called of three-dimensional cubics, let's say with Picard equal to Z, you will notice that they are rational if and only if the monodromy operator of this very singular fiber, which is always only 1, in the case of three-dimensional funnels, is strictly reported. So rationality of this funnels correspond to the fact that this monodromy is important. So I must admit that this is really a stupid theorem, which is proven that we know what's happening with the funnels, and we know what's happening with the monodromies, and we just compare and see that indeed we have this correspondence. So I hope by the end of the talk we actually get a little bit more conceptual understanding. Now, I told you what the mirror symmetry, and that is a really good point that gives you a way to think about this and make get some ideas. But since mirror symmetry is not proven, what I'm going to do is try to forget everything that I have said and try to record the information that comes from mirror symmetry in a different way. Any questions? Well, to do this, we remember that actually our cubics that we want to study, besides being algebraic variety, are also symplectic manifolds. So they have a symplectic form on them, which is the restriction of so-called Birational metric on P4 in this case, in the three-dimensional cubic, to these manifolds. So now, instead of looking at this mirror, what we are going to do is we are going to think about our manifold, X, the cubic, as algebraic variety, but also as a symplectic manifold as well. And the interplay of these two theories is what we are going to try to explore to get this new birational invariant. So once again, we forget that there is a mirror world, and we think of X as an algebraic variety given by this hypersurface, some other way. But we impose on it additional information coming from it, taught as a symplectic manifold. Now, in this particular talk, because I just wanted to look at the example of four-dimensional cubics at the end, so this theory that I'm going to associate with my symplectic manifold is going to be Gromov-Witten theory. But you can change that and use different theories to impose on already existing structure on your algebraic hypersurface and get different results. In particular, if you want to study different questions, for example, the question about G non-rationality, maybe rationality with respect to some group function, then the theory to impose is not Gromov-Witten, but so-called Chen-1 of homology. So, depending on what question to study, you impose different conditions on that. You can also try to impose just Sullivan homology, and I think that has some unexpected consequences as well. But so far, all we want to do is to remember that we have the round theory associated with X and impose on this X, on this hypersurface, the theory that we can get, the structure we can get from the symplectic geometry associated with it. So we forget everything about this mirror symmetry correspondence that I have mentioned. And all we need to remember is that actually there is a function, psi of u, which gives you a way to compute the number of rational curves of different degrees associated with these funnels, with these cubics. And this function satisfies so-called quantum differential equation. So where k is the operator of quantum multiplication, and then g is some really grading operator. In the case of three-dimensional cubic, which is our reference point, this matrix K is given like that. Mistaken, and G this grading operator. So if we solve this differential equation that I have mentioned there, so you are going to get a solution which counts the rational curves of different degrees which are contained in this cubic. Now, what we want to do is to record the information about this singular fibers, and the fact that when we blow up, there is a new singular fiber that doesn't interfere with this, in the language of this differential equation. So we forget about any mirror symmetry. Everything comes down to the information which is recorded by this differential equation. So now I'll just mention the result and then give you an idea of what goes behind the proof. So basically, what the theorem says is that we do get out of this differential equation a splitting of the de Rham homologies of our variety labeled by the eigenvalues of the quantum multiplication. And so these pieces on which this is split, these splits are going to be both elementary pieces, eventually atoms. And this splitting is a birational invariant modulo contributions of subvarieties of Paul mentioned 2 and high. So that is the thing that we want to get out of this structure that we are studying, and the splitting of the homology, of the de Rham homology of our initial manifold coming from the imposing the information of the symplectic part of this manifold, will shape to be a birational invariant. That's what we want to obtain, and that's what we are going to use to study the geometry of 3 or 4-dimensional cube. Any questions?
What's the 4-dimensional space?
Very good, actually. Thank you. It's the algebraic cycles on this cubic.
What's the 4-dimensional space?
H0, H2, H4, and H6. The space of algebraic cycles. Really good question. So, now I will, so we're returning to this, and so every time we impose additional structure, but it's about the same thing, just every time with a little bit more structure. I think that that's the best way to talk about it. So indeed, there is, ask this question exactly at the right moment. So what we are going to do now is build a certain Higgs bundle, which is going to record the information of coming from the quantum differential equation. So the base of this bundle is the space of algebraic, or if you like, PP cycle, depending if you believe or don't the Hodge conjecture. And so over this base, we consider the cotangent, the tangent space, T of f of x, and we consider an Euler field defined as the quantum multiplication plus this shift coming from the multiplication by delta I, which happen to be a basis of the chosen basis of algebraic cycles. In this particular case, we have 4 of them, and Ti are the parameters associated with this space. So here is our space of algebraic cycles in this case, and then over each point we have the homology of our homology of our variety, let's say the cubic, and then we have the splitting depending what are the eigenvalues of this Euler field associated with this point, namely here the parameters Q1, Q4 in this case. And so over each of these bases, we have a different number of eigenvalues, and this is the finite covering, which gives you this spectral covering of over our base. So the geometry of the quantum differential equation is recorded by this covering coming from the eigenvalues of this Euler field associated with different choices of Ti.
What are the eigenvalues of a vector field?
I think of this as a Higgs bundle, and then this Higgs bundle gives me so the determinant of this bundle minus the trivial section gives me a covering, and then the eigenvalues at each point, or if you like, the points of this covering and the eigenvalues of this field, or if you like, the geometric interpretation of the eigenvalues of the Higgs bundle. All right, so we can also think of this as a corresponding D module, and these are the singularities associated with it. So that's the picture that we want to keep in mind. And then the splitting of the homology is something that we are going to be calling local atoms. So if we take away the ramification divisor, so what you are left with here is splitting of the homology on local pieces of the outside this ramification divisor. And for these local pieces, in other words, the correct component of this spectral covering are going to be called atoms. So the pieces of the homology corresponding to the spectral covering, to the components of the spectral covering outside the ramification divisor are going to be called atoms. So in the case when this is something of general type, or Calabi-Yau, meaning that Kx is net, the atom actually consists just of one component. We have only one atom, and that is going to play an important role in our considerations. So the important thing is that we associate with this splitting of, with this choice of base of these algebraic cycles, splitting of the homology of our manifold coming from the eigenvalues of this Higgs field, and this happens to be a birational invariant. Now, so I want to point out that from here you can actually build a little bit more general theory. So this is the next upgrade of the theory based on the wonderful theorem by Hiroshi Ritani, who proved that this called in the paper F bundles, but I don't want to go into this definition. This Higgs field that we have just described splits in the following form under the ball. We have some piece coming from X, and then n-1 other pieces coming from the things that we blow up. And so this is one type of relation that we introduce, and then there is a certain quantum relay-ish statement that we have in this case proven by Hill and Cox, and also treated by Ritani, which allows us to consider this isomorphic classes of atoms. So in other words, besides these atoms being, of course, certain pieces of the round homology, they happen to be also non-commutative core structures, and then, of course, representations of the amount of the group as well. So this is just for the information expert. All right, so we get this splitting of the homology, and this splitting is a birational invariant. That's what we need to remember. So now, any questions?
Where do you get the spectral sequence?
Which spectral sequence?
Related to Ray Herschel.
Yeah. So, so what we have here is not a spectral sequence, but so this is the way this Higgs bundle behaves if I have P1 or Pn bundle over my initial manifold X. I have a splitting of the atoms, or if I have these Higgs bundles following this P1 or Pn bundle over this X. So if this is P1, basically I have a repetition of the homology, or if like of the atoms of the bundle, one for the zero homology of P1 and the other for the two homology of P1. And that's for all Pns. This splitting we call the Ray-Hirsch splitting. Yes.
What kind of object is the atom?
Once again, so it's a piece in the de Rham homology of your initial variety.
So in your picture, it kind of looks like it's not a linear subspace of the de Rham homology. It's just some.
No, it is a linear subspace.
But you said it's the components of the complement of.
Yeah, so in the case of P2, so it's basically one for the zero homology, one for the second homology group, and one for the fourth homology. Yeah, really linear. So in other words, if you look at the fourth diamond of P2, these are the corresponding atoms, which happen to be, as I said, non-commutative force structures, but also representations of the amount of the group, which is also.
And those atoms appear in that picture of the this Higgs bundle over the.
Yeah. So these are the. So you have a covering, and over each point you have certain eigenvalues, and to each eigenvalue you associate a piece of the homology. Other questions? All right. So now, in order to make this a little bit more connected with Hodge theory, we need to associate additional invariants with these pieces in the de Rham homology. So I must say that this is just scratching the surface, I mean, because I said that this is really a splitting of the de Rham homology only as vector spaces, but actually you can impose additional structure, and so using the gamma conjecture, which is proven up to dimension 2, make this really Z Hodge structures with the corresponding matrices, and make even stronger invariant. And then you can associate some torsion with it, and so on and so on, but that's not what we are going to do in this talk. So all we need to remember is that so with these pieces, we can, because they are Hodge structure, we can associate their rank, and of course certain Hodge polynomials standard in the Hodge theoretic considerations, and just to lead to the example of the four-dimensional cubic, we would like to point out that we are going to look at the coefficients from the t-square for this Hodge polynomial. So,
So what's the condition of an atom that's not irrational? Does not appear in.
so yeah, so, that it doesn't. I mean, so if this is a variety of dimension n. So this atom should not be an atom of subvariety of codimension n minus 2.
Complex.
Yeah. And if you look at this Hodge polynomials, then so you can briefly notice some classical fact from the Hodge theory of surfaces, which were discussed yesterday, and a little bit about the resolutions of singularities if these surfaces are not smooth. And the important thing to remember is that the rank of the homology group, sorry, I apologize, that's true, but of this atom that can participate in this splitting, if this is an algebraic surface, is at least 3. And so now, if we actually compute what is the number of algebraic cycles associated with this atom appearing in the, this is answer of Dennis's question, that this should be something that cannot be found in four-dimension 2. So if we can show that this rank, in the case of four-dimensional cubic, is less than 3, then this cannot be something that comes from algebraic surface. So that's what we proceed in trying to do. So, so we look closer to the example of four-dimensional cubic. So we have the following four eigenvalues associated with this Higgs bundle. So we have splitting of the homology of the four-dimensional cubic in these four pieces. One looks very much like the homology of a K3 surface. This first one, 120, 1, 1, 1. And then we have three others. So, now what we want to do is to try to decide what are the properties of the Koch polynomial associated with this atom in the middle. And the important part of this is that its rank, which is the number of algebraic cycles associated with this piece, is equal to 2. So if you have an algebraic surface, it has at least 3 algebraic cycles in H0, in H2, and H4. So therefore, this cannot be coming from an algebraic surface, and that's how you conclude, using of course the splitting is a birational invariant, that four-dimensional cubic cannot be birational. So you have this splitting, which is birational invariant, and then you look a little bit closer to this atoms, I mean, study their Koch polynomials, and you notice that the rank in this case is less than 3, and that is only conclude with the four-dimensional cubic is notation. So now, as I said, this is a very simple version, basically considering only splitting as a vector spaces. If you enhance this a little bit by putting the Z structure on this Koch substructures, you can actually prove the generic cubic containing a plane is not rational as well. In fact, since Stony-Brook Martin partner is the strongest in Koch theory, starting with Dennis and getting to, I don't know who is the last Koch theorist that you have hired here. So this theory of atoms should be really considered as a Koch theory of some sort, enhanced Koch theory, which will carry everything that you know from classical Griffith's theory. And you take some book on Koch theory and take a theorem, let's say, Schmidt sequence or something like that. Everything like that can be actually formulated in this atom setup. Let me though do something that is a little bit different, and that is look at this differential equation a little bit different. So now, a small historical remark here. So there were two types of theories which were developed in the same city at the same time. One was the theory of singularities developed by Arnold and his group, and the other was conformal field theory. Alexander Zamolodchikov is in this university. So that was done by him and Knizhny. But these groups didn't quite communicate, and so there were two things which were the same, which are the string spectrum and so-called arc charges in conformal field theory, which happen to be the same in many cases, but that wasn't noticed by these groups. The person who actually noticed this is Kumrun-Waffa later, and he actually connected this with certain asymptotics of solutions of differential equation. I mean, in the physics way, I don't think he cares about rationality, but he definitely did this in his work, and it's really fantastic work together with Chekhov from Kumrun-Waffa.
What?
Kumrun-Waffa.
So which arrow is that with connection?
I mean, he explained in the case of Newton-Lochkov equation all of these connections in his joint paper with Chakotay around 1990. This is before Mirror Symmetry. So, and so now that's what we are going to do in this case, but not in connection with finishes of Walsh-Proof equation, but in connection with this quantum differential equation that we already have considered. And so we'll look at the solutions of this equation and their asymptotics when it comes to sub-exponential growth solutions. And so now, this using this atoms, one can show that the asymptotics of these solutions are actually birational invariants. And you can come up with a formula for computing this asymptotics in the case of quantum hypersurfaces, like in the case of complete intersection in weighted projective spaces. But I was lazy and I wrote the formula only in the case of hypersurfaces in Pn. And this is the way this formula works. So this is the highest asymptotics, delta. You can play with the others, also the way they relate to each other, something that is very well done in formal field theory. I will not talk about this. But so this higher asymptotics is computed by the formula, delta is equal to dimension, times n minus d over t, where d is the degree of the surface. And so if you compute what you are going to get in the case of three-dimensional cubic, so I did this calculation for you, you get 5/3. And the theorem tells you that if this delta is bigger than the dimension of x minus 2, which in the case of three-dimensional cubic is exactly 1, so you can put in a different way that this cubic is three-dimensional cubic, it's not rational. So now, in case of four-dimensional cubic, you're going to get that this number delta is equal to 2. So that criteria doesn't give you any information, but I already explained how this could be done in terms of this atom theory. Now, once again, I mean, this is just scratching the surface. There are many other invariants one can draw from here. So I won't do that, but I will just show you one more application. And that is the case of G-invariant birational geometry. So this is, again, a part of birational geometry which became very popular these days due to the work of Jinkel, Jozov, and their collaborators. But it's really very classical. I mean, so I remember I was probably third-year undergraduate when Iskowski posed this question about non-rationality of a hypersurface of degree 1, 1, 1, 1 in P1 plus P1 plus P1 plus P1 with the action of some group. Meaning, when I say G-rationality, this just means that we consider only birational transformations which are invariant in the direction of this group. So now this variety, the 1, 1, 1, 1 hypersurface, is known to be rational because it is a blow-up of P1 plus P1 plus P1 in the elliptic curve, so it's definitely rational. But you can use the theory of atoms to study the questions of G-rationality. And the way this works is, instead of considering the whole space of algebraic cycles, you consider only ones which are equivariant of the reduction of this group. So this reduces the directions in which you can move, and therefore many of these eigenvalues come together of the corresponding Higgs field, and that allows you to conclude that this funnel, which is certainly rational over the complex numbers, overfilled with the Laurent group, which is a subgroup of, well, let's say a group which has sensitively on the 1111 is not going to be actional, which was a classical question. Right. Geometry partial answer in different situations were given by Kuznetsov and Prokhorov and by Chingel and Shultsov as the full answer to this question. But this is just one example in a paper which appeared a month ago. We give many other applications. So now one must say that this method is a little bit different from what I have described. I give you just the answer here, but instead of from Witten theory, you use Chen-Wang homology in that case, which is really created in order to study this theory in the case of group functions. Thank you very much.
Further questions?
Yes.
You promised something about cubic.
Yeah. So quintic.
No, cubic dimensional five.
But yeah. All right. So now we if so we need to work a little bit harder, and so there is an additional approach theory that needs to be developed with these skills here. So now, already long time ago, in 2007, there was the idea that you actually split the Landau-Ginzburg model. So in the case of five-dimensional cubic, so the index is 5 there, sorry, 4 there if I'm not mistaken. No. And then what you are going to get is that this corresponding fibration is a fibration of elliptic curves over something 4-dimensional. But instead of working with numbers, you actually work with divisors in C3, and that's what records the information of the non-rationality. I don't know what to say. This is not, I think it's checked, but in this case, I mean, you did have this superposition of hypergeometric classical local systems, something that Boykers and Kostarika work, and then the way you actually put them together happened to give you this birational invariance. And of course, I don't want to speculate, but yeah, there is some reason to believe that generic one is not rational because of these numbers. No, because of these devices. So I have a little bit of a problem here. If what I said is correct, there's this conjecture of Kuznetsov that cubic dimension 4 is rational if and only if there's a commutative K3 appearing in a semi-orthogonal convolution. These things do not fit together very well, so I'm reluctant to say anything about that at the moment. But maybe if Kuznetsov conjecture is correct, one is to think a little bit. Yes?
You mentioned at some point that you can place homomorphism in a German class solution.
So, I mean, I think we should birational geometry with Dennis here. You want me to explain just very well in front of him? That's not going to help.
I'm just asking what's
I don't go for this.
That was not an innocent question.
No, I understand. But actually, in private, I'll be happy to discuss.
This idea that Rudolph theory is some kind of quantum deformation.
Yeah, he's right. Yeah. I mean, actually, you should pursue this. Yes.
Here's the question. When you mentioned Higgs bundles, Higgs bundles over X.
Yes. No. Over H. So, I mean, so you choose piece of the homology with all the structure it could carry, some mixed core structure or anything, and then over this base, we consider this Higgs bundle, T module, or whatever you want to start. So actually, I didn't mention this, but this is also very good for starting questions about non-rationality over fields with non-trivial transcendental degree. And then this, our guide to the theory enters really the game. You get abstractions which are not numbers like here, but really some supports of this T module that you associate in this. And so that's what you can use in this. So, but the base is is part of the homology of your initial variety. Now, I must say that I use only algebraic cycles, but you can actually use homology and even more interesting phenomena that are happening there, but this is for another talk. So you get further treatment.